So now I'm going to show you an alternative way to calculate the pI for the peptide kite. So last time what we did is we calculated the charge of each ionizable group at each pKa, and then we found where we go from plus 0.5 to minus 0.5. You may be wondering why I did that, so I'll go ahead and show you my rationale and another way of calculating the pI. All right, so here we have our peptide kite, and I've went ahead and I've written the pKa's for each ionizable group there. Now, if we were to look again at the titration curve for kite, we would have 4 potential pKa's to look at. So we have a pKa of 2.0 for the C-terminus carboxylic acid. We have 4.2 for the R group of the glutamic acid. We have 9.5 for the N-terminus and 10.5 for the lysine side chain NH3+. Now, the question we want to know is between which two pKa's does our peptide have a net neutral charge? So there's 2 different approaches we can take. The first that we can do is we can find the 2 pKa's and we can determine the region because we know it's the region bracketed by going from a chart where we switch over from being positively charged to negatively charged. The other approach we can take is we can selectively pick pKa's that are on the outside, or pHs that are on the outside of each pKa, to then find the region where we're positive, where we have a net charge of 0. So we can go ahead and try that now. So let's say, if we want to find out, so one pH we can do for the region below the first pKa of 2 is 1. If we want to pick a pH between 2 and 4.2, we could pick a pH of 3. If we want to go between 4.2 and 9.5, we can do 6. And then we want to go between 9.5 and 10.5. That's cutting it a little close, and this is one of the reasons why I'm a little leery of this method. But we could say perhaps pick maybe 10. And then above 10.5, we could pick 12. Okay, so if we're at a pH of 1, remember we set up our convention. pH equals pKa. We go from 0 to 14. We're protonated below the pKa, and we're deprotonated above the pKa. So if we look at pH of 1, we're going to be below the pKa for all of our groups. So all of our groups are going to be in the protonated form. If we look at the protonated form of a carboxylic acid, it's neutral. So all of our carboxylic acids are going to be neutral below their pKa, whereas if we look at the amine or a positively charged amino acid, the equilibrium, the deprotonated form is neutral and the protonated form is positively charged. So both of these would be +1. Now, if we go to 3, we're between, so we can actually write in that we're going to have a net charge of, let's go ahead and let's erase that because we have to do the total charge at the bottom, my bad. Setting up a chart. By the way, if I ask you to do this in class, you won't be given a chart. You're going to have to figure it out yourself. So below the first pKa, we're going to have a charge of +2. So now, if we look at pH 3, where we're between the first pKa and the second pKa. So at a pH of 3, our C-terminus is now going to be deprotonated, so it'll have a charge of -1. If we look at the side chain glutamic acid, we're still below the pKa of 4.2, so it'll be neutral, whereas both of our NH3s are going to be positively charged. So now we're going to have a charge of +1. So between 2 and 4.2, we have a charge of +1. Now, if we go to 6, both of our carboxylic acid groups are going to be negatively charged because they're going to be deprotonated, but both of our amines are going to be protonated because we're still below the pKa of the N-terminus amine and the lysine side chain amine. So we're going to have +1. So those charges cancel out, and we're going to get a neutral charge between 4.2 and 9.5. At 10, we're above the pKa's of both of our carboxylic acid groups, and in fact, We can go ahead and fill that out for 12 as well because we're nowhere above the pKa for both. But things get more tricksy when we're looking at the amines. So for the N-terminus at 10, we're above the pKa. Now, we're not 1 pH unit out, but we're going to make the assumption that even a half a pH unit out, the deprotonated form is still going to be dominant. So we would go with a -1 here, or we would go with the deprotonated form would be dominant, so we would go with a neutral here, because if you remember, H3N plus, we deprotonate that, it's neutral. But the lysine is still going to be mostly protonated at that point. So we would have a charge of -1 here. And then finally, when we're at a pH of 12, we're above the pKa of the N-terminal amine, so we'd have a 0 charge again, but now the lysine is also going to carry, the lysine side chain is also going to carry a net neutral charge and be deprotonated, so we'll have a total charge of -2. So we'll be -1 and -2 over here. And so if we identify that region where there's a 0, we would go out to the 2 pKa's that bracket that region and then take the average. If you want still another way of looking at how to think about this, is we can take each of the pKa's and we can figure out what the charge of that group is below and above that pKa. So we start with a pH of 2, or we start with the carboxylic acid for the C-terminus above, so that's its pKa. So when we're below the pKa of 2, the protonated or neutral form dominates, and above a pH of 2, the negative form dominates. And then as we go up the pH scale, so below 4.2 and above 4.2, our C-terminus is still protonated, and deprotonated will continue to be deprotonated or negatively charged all the way up the pH scale. Now, if you look at our glutamate side chain, below a pH of 2, it's neutral, and immediately above a pH of 2, it's still neutral. We hop over to 4.2. When we're immediately below a pH of 4.2, the deprotonated form still dominates, but when we pass 4.2 and we flip over, that's when we begin to see the deprotonated or the negative form dominate. And the negative form will still continue to dominate at those pHs surrounding those higher pKa's. For the N-terminal amine, we're going to be protonated or positive all the way up until we approach its pKa of 9.5. So immediately below the pKa of 9.5, the positive or protonated form will dominate. Once we flip past that pKa for the N-terminal amine, though, of 9.5, we're going to see the deprotonated or the neutral form dominate, and will continue to dominate as we go up the pH scale. Finally, for the lysine side chain, it's going to be protonated again and have a charge of +1 until we approach its pKa of 9.5. And immediately below that pKa, it's still going to be positively charged, but once we go above that pKa, we're going to switch over to being neutral. And if we go up and we tally all of these numbers together, we can see that when we can go and we can pinpoint the region where we're 0, put a nice little box about it, and you can see that the region where the total charge is 0 is bordered by 4.2 on one side and 9.5 on the other side. And you could take the average of the 2 pKa's and then get a pi of 6.9. All right, so those are 2 additional ways of thinking about and calculating pi. You can take whichever avenue of the 3 potential routes I've shown you that helps you understand it the best.